waves topic, section 7.13 is about the Doppler effect. So the definition for the Doppler effect or the Doppler shift is an apparent increase or decrease in the frequency of a wave caused by the relative motion between a wave source and the wave observer. Let's break this down a little bit. All right, what are we talking about with all these words here? First of all, the Doppler effect can happen to any wave, but the waves that we will be talking about will be either sound waves or light waves. Now, if you increase the frequency of a sound wave, you hear a higher pitch. The frequency of a sound wave is directly related to the pitch. So, a low frequency sound wave would sound low, and a high frequency sound wave would sound high. That was awful, but you get the idea. All right, now, the frequency of a light wave is going to be the type of light or the color of the light. What we're going to perceive, because the only kind of light that we can perceive is visible light, we will perceive a change in the color. So for example, high frequency light would be shifted toward blue or purple, and low frequency light would be shifted toward red or orange. Okay? So if we're shifting toward a higher frequency, the light is going to look more toward the purple end of the visible spectrum. If we're shifting toward a lower frequency, the light is going to look shifted more toward the red end of the spectrum. All right, so again, frequency of sound waves, all right, the frequency is directly related to pitch. Low frequency is a low pitch. High frequency is a high pitch. All right, and the frequency of light waves, is related to the color of the light. So we've got the word frequency, we know what kind of waves we're talking about. Okay, relative motion. All right, what that means is it doesn't really matter whether the source or the observer is moving. All right, let's talk about sources and observers, and then we'll go back to relative motion. Source, observer. Okay. A typical source of a sound wave would be a police car siren. This is going to be a terrible drawing of a car. Bear with me. All right, here's the car. There's the wheels. All right, there's the siren up on top. All right, the police car could be the source of a sound wave. All right, the sound wave is coming off the siren. Right? All that noise. That's the source of the noise. All right, the observer would be a person, all right, standing wherever, a block away, 10 feet away. The observer is a person. Remember, you can observe using any of your senses. You can observe using your eyes. You can observe using your ears. You can observe by touching. You can observe by tasting, etc. Smelling. All right? So this is a source of a sound wave. And the observer hears the sound wave. Now, a source of a light wave could be a star. The star gives off light. All right? The star is a source of a light wave. And the observer can look at the star with his eyes, all right? Or, I guess he needs ears if he's going to hear the sound wave. The observer can look at the star with his eyes, or the observer might want to use a telescope, all right, to look at the star down there. All right? So a typical source of a sound wave, a typical source of a light wave, a typical observer is you or I, using our eyes, using a telescope, using our ears, etc. Now, relative motion. When we say relative motion, we mean it doesn't matter if the guy is standing still and the car is moving toward him, or if the car is standing still and the guy is walking toward the car. It doesn't matter. There is relative motion. The distance between the source and the observer is changing. Now, if they were both traveling in that direction at the same speed, then there would be no relative motion between them. Okay? The distance between them would stay the same. If the car was traveling very slowly, 3 miles per hour, and the guy was running or walking very fast at 3 miles per hour, then there would be no relative motion between them. All right? No relative change in that distance. Okay? But if one or the other is standing still and the other one is moving, right, toward the other one, there is relative motion. Same thing with the star and the observer. It does not matter whether the star is standing still and the Earth is moving, the Earth with the observer on it is moving toward the star, or the Earth is standing still and the star is moving toward the Earth. It doesn't matter. There is relative motion between them. All right? Okay, so now here, the important part. Because of the relative motion between the source and the observer, there is going to be an apparent increase or decrease, an apparent change in the frequency. Now, if I'm running toward the police car, is that changing the pitch of the siren? No. But does it sound different? Is there an apparent increase or decrease to the frequency? Let's say, for example, when the police car is coming towards me. All right, so if the police car is coming towards me, let's say the police car, let's say the pitch of the police car's siren is all right? All right? Now, when the police car is coming toward me, that doesn't change the mechanics or the electronics of the siren. The siren is still emitting, but when it's coming toward you, it's going to sound higher. When it's driving away from you, it's going to sound lower. All right? So the increase or decrease in the frequency, the pitch of a sound wave is apparent. It's not real, but it sounds different. Okay? And the same thing goes with the light. Let's say that the star is giving off, for example, giving off green light. All right, that's the color the star is giving off. All right, now, if the star is, let's say that the person here, the Earth is not moving, just for argument's sake. If the star is going toward the person, then that green light might look violet. Okay, so when the person looks at the star is going to look bluish or violet, or toward that end of the spectrum. If the star is moving away from you, then it's going to look reddish. Okay? So now keep in mind, the star is still giving off green light, but because it's moving toward or away from the observer, its apparent color is going to be either more toward bluish violet or more towards an orangey red, right, toward that end of the spectrum. All right, so again, now we're going to look at all of this in much more detail. But I want you to understand the word apparent means that The siren isn't really changing. The color of light from the star isn't really changing. It's the way it appears to the observer that seems different. It's real. The change is real to the observer, right? But you can almost say that his eyes and his brain are playing tricks on him. All right, so it's an apparent change, an increase or decrease in the frequency. Keep in mind the frequency of a sound wave is the pitch. The frequency of a light wave is the color. All right? It's caused by relative motion. All right? They're either getting closer together or getting further apart. They're not traveling together. If they were traveling together, there would be no Doppler shift. Okay? But they're either getting, again, relative motion, closer together, all right, or farther apart. Okay? And it is between the relative motion of a source and an observer. So now you know a typical source of a sound wave, a typical source of a light wave, and a typical observer. Okay? So we're going to go into some more detail. All right? We're going to get rid of this, and we're going to go into some more detail. Now, I'd like to show you just a little bit about how we draw, how we represent or model waves. Now, I'm sure you recall that sound waves are a type of longitudinal wave, right? Longitudinal wave. So sound waves are longitudinal waves. So they have compressions and rarefactions, compressions and rarefactions. If you're going to draw a sound wave, one way to draw a sound wave would be like this: compression, rarefaction, compression, rarefaction, compression, rarefaction. In other words, they're close together, far apart, close together, far apart, all right? And the wavelength would be from compression to compression, right? Or from rarefaction to rarefaction. In either case, the length would be the same, all right? From here to here is the same as from here to here. All right, so let's call this a short wavelength. All right, so from here to here is a short distance. Now, if I'm going to draw a longer wavelength sound wave, all right, then compression, rarefaction. It's further spread out. Compression, rarefaction. All right, so this wavelength of this sound wave is longer. Compression to compression, all right? This wavelength is shorter, this wavelength is longer. This is how you draw a compression wave, a longitudinal wave, a sound wave. Now, this would be a pain in the neck to try to draw, all right? It's just a pain in the neck to try to draw. An easier way to represent, right, all waves, but it works really good for sound waves, would be to draw wave fronts. I'm going to make, all right, a line like that for each compression. So I'm going to put a line there, I'm going to put a line there, I'm doing it like a semicircle, all right, part of a circle, all right, a line there, all right, a line there, and there would be another one out here someplace. All right, I'm trying to keep the wavelength uniform. All right, so I'm showing, these are called wave fronts. All right, and it's just showing where, if you had a source of a sound over here, something over here, the police car is over here, it's making a sound, all right, and the sound waves are traveling outward from this point. All right, so you've got like a semicircle coming out and marking each compression, 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 compression. But it's traveling outward, all right, here, 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 outward from this center point here. All right? So you can draw sound waves as wave fronts, and what's more important is that if you draw the wave fronts close together, That's a short wavelength. Let me show you. All right? Here's the police car's siren. All right? Here's the siren. All right? If it's a high pitch, high frequency, then the wave fronts are closer together. If it's a low pitch, low frequency, then the wave fronts are going to be further apart. So this would be ah, this would be ooh. Okay? Remember, the frequency of a sound wave is the pitch. Right? High pitch, ah, low pitch, ooh. Okay? All right. So we can draw sound waves as wave fronts, and it will show whether it's a high frequency or a low frequency sound. You can do the same thing with light. All right? If you have a star, all right, and it's giving off a high frequency light, okay, you can draw them close together because that's showing your, all right, your crest, 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 crest. All right, so wherever there's a crest, you're drawing a wave front. All right, crest, 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 crest. Let's call this high frequency. If I spread them out, it's low frequency. So this could be purple or violet, high frequency light. All right. If the star is giving off red light, all right, it's going to be a longer wavelength. Okay. So we're just going to spread them out more. This would be a wave front shown as a longer wavelength. All right, so that one could be like this. Crest, 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 crest. All right? Crest, 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 crest. Okay? So I will be showing these curved wave fronts as a diagram, and that gives you an indication of the frequency of the wave, whether it's a sound wave or a light wave. Right? The wave fronts can tell you the relative frequency. Right? If it's a long wavelength, it's a low frequency. Ooh. If it's a short wavelength, it's a high frequency. Ooh. Right? Or purple. Okay. Low frequency, all right, red or low sound. High frequency, purple or high pitch. Okay. Moving right along. So, let's start with sound waves and how the Doppler effect affects sound waves. Here we have a police car, and the police car has a siren on the top, and the siren gives off a sound of a steady pitch. Let's say it's ooh, all right? That's the frequency or the pitch of the sound wave. So I'm going to draw that sound wave like this, all right? And when that sound wave reaches our observer, all right, here's a person standing over here, all right, on the sidewalk, all right, and that person needs ears. Can't hear the sound wave without ears. All right, now let's say that the police car is standing still and the person is standing still. All right, so here comes the sound wave, the siren. And that's the pitch that the person hears. Now, the person is going to hear that pitch whether they're both standing still or if they're both moving together at the same speed and the distance between them is not changing. All right, so it doesn't matter if they're both standing still, all right, the distance between them is not changing, or if they're both moving at the same speed. It doesn't matter if they're going this way or they're going this way. If they're both moving at the same speed, then that person hears the correct pitch that's coming from the siren. Now, let's change things up a little bit, all right? Let's have the police car driving toward the person, all right? Now, what happens is when the source, remember, all right, this is the source, and this is the observer. Let's get rid of those. This is the observer. All right. Now, again, I said this earlier, just because the police car is moving, that does not change the actual pitch of the sound coming off the police car. It's still ooh. But if the police car is driving toward the person, what happens is the sound waves, for lack of a better explanation, get scrunched up. And the person hears that higher pitch, that higher frequency. So if the police car is going toward the person, it's going to sound like this. Eee, higher. It's going to sound at a higher pitch. You see these wave fronts, all right, are closer together, all right? The person thinks, the person hears a higher pitch. That is the apparent frequency that the person hears. It seems higher. It sounds higher, right? The sounding higher part is real. It's just that the siren itself hasn't actually changed. It's still giving off whoo, but this person is hearing hee. I don't have a better way to do this. All right, now, what if, on the other hand, now remember, when they're getting closer together, the sound waves get scrunched up, let's just say, and the wavelength is shorter, so this is a higher frequency. Okay, now, what if, instead of moving toward the person, all right, what if the police car is moving away from the person? All right, here's the person standing on the sidewalk. All right, he's got his eyes and he's got his ears. And the police car, all right, is still, oh my God, this police car is getting worse and worse. The police car is still giving off the sound at the same pitch. The siren hasn't changed. All right, it's still woo, but because the police car is driving away from the person, it's spreading out the sound waves. And it's going to look more like this. All right, here's your wavefronts. They're more spread out. All right, so the person is going to hear a lower pitch. The person is going to hear ooh, a lower sounding sound. Okay, now, it doesn't matter. It doesn't matter if the police car is going that way or the police car is standing still and this person is, let's say, in a car with the windows rolled down and driving away from the police car. As long as the distance between them is getting greater, the wave is going to get spread out and the person is going to, the pitch, the frequency that the person hears, the apparent frequency, is going to be lower. Okay? Now, the two examples I just gave are assuming that the police car is traveling at a constant velocity. He's going toward the person or away from the person at some specific speed that's not changing. All right? Now, let's look at the example of light. All right, now let's do the example of a light source. All right, let's say that there's a star, and the star is giving off green light. And here's a person on Earth, and that person has a telescope, and that person is looking at the star. All right, now the star is really giving off green light. But if that star is moving toward the Earth, all right, now the wave fronts from the green light might look something like this. All right, there's your green light. Okay? And notice I'm keeping them the same distance apart. Okay? All right, so the wave fronts from the green light would look something like that. But if the star is moving toward the Earth, toward the person, those wave fronts get scrunched up. All right, and when the wavelength gets shorter, the frequency gets higher, and we know that the frequency of light determines the color, the color of the light. So if those wave fronts get scrunched up, the light is going to appear, all right, like a shorter wavelength, higher frequency. So the wave fronts are going to look like this. They're going to look closer together, all right? And I'm going to try to keep them, there's crest, 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 all right? They seem closer together than before, all right? I probably should have made them a little bit closer together. But in any case, you get the idea. All right, now, that's if the star is moving toward the Earth. If it's moving toward the Earth, the wave fronts appear to be scrunched together, a shorter wavelength. You're seeing, what you see is apparently a higher frequency. So the star looks bluish, purplish, right? It's shifted toward the high frequency light colors. All right, now, what if that star is traveling away from the Earth? All right, let's just make the Earth stationary, all right? And the star is moving away from the Earth. All right, so here's the star. The star is really giving off green light, let's just say. But since it's moving away from the Earth, those wavelengths get spread out, all right? And it's going to look something like this. There's your transverse wave, right? Your light wave. And there's your wave front. There's your wave front. All right, this is a much longer wavelength, a much lower frequency. The star looks reddish, orangey, red, all right, toward that end of the spectrum. Okay? Now, all right, quick little review. All right, in terms of sound, okay, if the distance is decreasing, right, between the observer and the source, in other words, they're getting closer together. It doesn't matter if the person is moving toward the source or the source is moving toward the person. If that distance between them is getting smaller and smaller, all right, you've got a relative change in the distance, all right? So you've got the frequency is increasing, all right? That's going to be a higher pitch. All right? We should probably do light. All right? If the distance is decreasing, the frequency is increasing. That's going to be a violet or a purple shift. Okay? So you're going to a higher frequency. Okay, I'll just draw the light wave. Right? You're going toward a higher frequency. It's a higher frequency shift. Toward a higher pitch, toward violet or purple. when the two objects are getting closer to each other. Now, if the distance is increasing, they're getting further and further apart. That means the frequency is decreasing. I'm sorry, the frequency is, frequency is decreasing, okay. All right, you've got a lower pitch for the sound. All right, if I were to draw the light wave, all right, there's your lower frequency, all right, and that's going to be a redshift. Okay? Now, this entire discussion assumes that the object that's moving, whether it's the source or the observer, is moving at constant velocity. All right, I don't want to get too complicated, right? So the object that's moving is moving at constant velocity. Now, what if one object is accelerating toward the other object? What if it's going slow and then faster, 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 faster? Okay? Slightly, we have to say a little bit more if one object is accelerating toward the other object. All right, so let's take a look at that possibility for both sound and light. Okay? Now, all right, before we do that, let me do one little demonstration. This is going to be horrible. One little demonstration of what happens when a police car comes towards you and goes past you. All right? Now, you know the police car siren has a certain pitch. Let's say it's woo. Okay? Now, when it's coming towards you, if you're standing still and it's coming toward you, all right, the waves are getting scrunched up, so that's a shorter wavelength, a higher frequency. All right, when it's coming toward you, all right, it's going to sound. All right, now I'm going to draw. I'll draw wave fronts. All right, so when it's coming toward you, it's going to sound higher. Right. So here's the police car where it starts. Here's you. All right, here's your ears. Okay. And then as it's going away from you, right, the sound wave gets drawn out. So as it's going away from you, you're going to hear a lower pitch. Okay? So what's going to happen, the police car's coming towards you, you're going to hear the sound go up in pitch as it's coming towards you and go down in pitch as it's going away from you. So it's going to be like, woo, right? It's got a certain sound. As it's coming toward you, it gets higher. And then as it's passing away from you, it goes down lower. Okay? One more time. Woo! You know that any siren, any sound going past you changes in pitch. You know that. Now you know why. All right? And you know when it's going to sound higher. All right? When the distance is getting smaller, it's going to sound higher, or it's going to look purplish. When the distance is between you and it is getting larger, it's going to sound lower, or if it's a star, it's going to look reddish. All right, now, that's for constant speed. All right, now, what if the object is moving toward you faster and faster, or away from you faster and faster? Okay, if the object is accelerating toward you, now that could be going, let's say coming toward you faster and faster, all right? All right, so you're here, all right? And here's the police car. All right? And it should be driving on a straight road. Oh boy. Lopsided police car. That's no good. Let's make that flat. Okay. All right, so here's the police car. And now good. Nice flat police car. Okay. Here's the siren. All right. Now, what if it is accelerating toward you, going faster and faster toward you? I don't much care at this point what the sound is actually coming out of the siren. What I care about at this point is how it changes. All right? It's coming faster and faster. So in the beginning, it's going to be closer together, but as it speeds up, it's going to get closer and closer and closer and closer. All right? So you see what's happening, all right, to the pitch of the sound. All right, let's move the little guy. Let's just put him over here so he's a little closer. All right, so what is this person going to hear when the police car starts far away and is going faster and faster and faster as it moves toward the person? All right, this is low frequency. The frequency is getting higher and higher and higher. So this person hears an increasing frequency. An increasing frequency. Okay? So it's starting out low, all right? Right? I shouldn't have dropped off there. All right? Okay? It's just going up. Low, higher, 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 higher pitch. All right? An increasing pitch. All right, now let's think about another possibility, because there are lots of possibilities. The one I just did, the police car was going faster and faster toward the person. Now, what if the police car is coming toward the person, and when he's here, he's going very fast. He sees the person, and he wants to slow down. He wants to come to a stop. He doesn't want to hit the person. All right? So let's take the situation where the acceleration is slowing down, all right, as he gets closer to the person. So back here, the police car is going very fast. All right, if he's going very fast, think about this. If he's going very fast here he's going to be going slower. He's going to come to a stop eventually. But right here, he's going very fast toward the person. Right? Are those wave fronts going to be close together over here or far apart? Which one when he's going very, very fast? What do you think? When he's going very, very fast, they're going to be close together. All right? So right here, they're going to be close together. All right? Now, he starts slowing down as he goes toward the person. When he's slowing down, then they're going to be further apart. All right? So what's going to happen is the wave fronts are going to start spreading out. All right? So what's going to happen to the pitch as the police car is going toward the person and slowing down, decelerating, if you will? It's going to sound a higher pitch to a lower pitch. So this is going to be decreasing frequency or decreasing pitch. All right? So it's going to be You get the idea. It's a high sound when he's going fast toward the person, a lower sound as he's slowing down, and somewhere around here he's going to come to a stop. He doesn't want to hit the person. All right? So the main point that I want to get across from this discussion of accelerating, an accelerating source or an accelerating observer, is that when the relative motion is a constant velocity, the different frequency you hear will be a different constant frequency. Boo, or boo, or boo, right? But if there's an acceleration involved, if the source or the observer, doesn't matter, is speeding up or slowing down, the frequency is either going to increase or decrease. It's going to be ooh or whoop. Okay? That's really all that I want to get across. Now, I'll do a little summary in a chart form of everything that we've talked about with Doppler effect. All right, so just a couple of important points about some of the things that we talked about. First of all, again, the word apparent. All right? The police siren, the pitch that comes from the police siren is not changing. The color that the star gives off is not changing. It's what the person thinks they hear. It's what the person thinks that they see. The pitch that they are hearing, all right? The color that they are seeing, all right? It's an apparent change. The actual source is never really changing, all right? That's first of all. Another important point is you want to be thinking about the distance between the source and the observer. All right? How is the distance between the source and the observer changing? All right? If the observer is standing here and the police car is here, and the police car is traveling at a constant velocity, right, then the waves are getting scrunched up because the police car is getting closer and closer to the person. But since the police car is traveling at a constant velocity, all right, that change in frequency, all right, there's one change in frequency there, all right? Now, if the person is standing here, the observer, and the police car is moving away from them, then those waves are getting drawn out, all right? So the wavelength is getting longer and longer, the frequency is getting lower and lower, right? The distance between the observer and the source, all right, is getting larger and larger, all right? Now, that gets a lot more complicated, or a little more complicated, when the police car is moving faster and faster toward the person, or slowing down as they come toward the person. But again, try to think about how the distance between the source and the observer is changing. All right, now, when sound, all right, has a higher frequency, it's a higher pitch. It sounds higher, right? A higher frequency is closer together. The wave fronts are closer together. Lower frequency, the wave fronts are further apart, right? That's going to be a lower pitch. For light waves, all right, a higher frequency is going to appear violet. It's going to shift toward violet or blue. All right, a lower frequency is going to shift toward the orange-red end of the spectrum. All right. If the changing, if the velocity, all right, is the same, is staying the same, then the different frequency that you hear is going to be a different constant frequency. If there's an acceleration, in other words, the velocity between the observer and the source is changing, then you're going to hear either an increasing or a decreasing frequency. That frequency is going to be changing, right? A different constant frequency or a frequency that is changing, all right? Now, just a quick little review of the pictures, all right? So you've got the pictures in mind of just the simplest examples, all right? The change with a constant velocity there, okay? So here's the police car, all right? All right, here's the observer, okay? He's got ears, eyes. Oh, all right. If the police car is moving toward, let's say that the observer is stationary, all right? If the police car is moving toward the observer, then what's happening? If the police car is moving toward the observer, all right, constant velocity toward the observer, the wave fronts are getting scrunched up, so it's going to sound a higher pitch, right? They're closer together than when they first started, right? If the police car is traveling away from the person, all right, everything's going to get spread out. It's going to sound a lower pitch, okay? Here's the star. Here's the person observing the star. Likely they have a telescope, okay? And here's the hat. All right, so the person is observing the star with a telescope. If the star is coming toward the person, the waves are getting scrunched together, so you're going to see a violet shift. It's going to shift toward the higher frequency, so it's going to look bluish, purplish, right, toward that end of the spectrum. That's if the star is moving toward the person. Right? If the star is moving away from the person, those waves are going to get spread out, right? And that's when you get a shift toward lower frequency, right? If the star is moving away, right, you're going to get a shift toward lower frequency that's further apart, okay? It gets spread out, and the star's light is going to appear red. That's a red shift. Okay? So if you just think about it, all right, and picture whether the wave fronts are getting closer together or further apart, you'll be able to answer these types of questions easily. I'll see you in the next section.